So this is the final review of series test. In this review, we can study one of the most actually two of the most important tests called the ratio and root test. So the ratio and root tests. So there are two tests. So the first one is what we call the ratio test. So let's write this as a theorem. So what it says, this is a ratio test. So we can take a ratio. It's a very powerful test. So let sigma an be a series. Then three things can happen. The first one, what we can do if the limit n goes to infinity of the ratio an plus 1, we divide two consecutive terms and take the absolute value of that. We're going to call that rho. If this rho is less than 1, that means the second term grow slower than second term is smaller than the first one, so it's gonna go slow. So in this case, what will happen, then the series an converges absolutely. This implies that the series converge. So the second one, if the limit n goes to infinity is the same one, an plus 1 over an, we take the ratio of the two consecutive terms, let's say rho, which is, if this is larger, then the series diverges. The third one, so what can happen sometimes, this term can be, the limit can be exactly 1. If the limit is exactly 1, this is rho, okay? So the Greek letter rho. If it's exactly 1, what will happen? The test fail, or you can say inconclusive. Okay, now the question is when we can use this. When to use. So let's say when to use. So this will be helpful. So for example, when you see terms like let's say some number to a power with like factorial terms, when you see factorial, this is the kind of trick that we use. And when you see like a n to the n, like terms like that, so we can use this one. So those are kind of two things that we definitely use this trick. But when you don't want to use this, like for example, if you see a linear term like this, like n plus 3, like that kind of linear terms, this may not gonna be good, because you see that like when you see ln, we don't use that. When you see like n squared, n cubed, like powers like that, we don't use these in these situations. The reason is when you try to take the limit, it's just gonna be 1. So useless. So but when you see factorial, like powers like that, we can use this. Okay, so let's see this in maybe 2 examples, how it's going to work. So the first example, so example number 1, so just say test for convergence. So the first one, sigma n going from 1 to infinity, negative 1 to the n cube over 5n. Okay, the 5n is the reason why we use this. So in this case, you can see that an is negative 1 to the n cube over 5n. Okay, so let's try the ratio. So it's a limit n goes to infinity, an plus 1 over an plus 1 means replace the index n by n plus 1. That's what it means. So it's a limit n goes to infinity. So we have negative 1 to the n plus 1. N plus 1, you replace n by n plus 1. 3 over 5 n plus 1. Okay, now we're going to divide by n. Divide means this is a fraction, that means multiply by upside down. That means 5n goes there, negative 1 to the n goes there, and n cube goes there. Okay, so you can see, you can simplify this a lot. You can see that this term goes away because this absolute value of these are 1, so we don't need that anymore. And also 5n cancels with 5n, so I'm going to cancel the n. So you can see that only 1 over 5 left, so we can take it out. So that means you can write this one as 1/5 limit, and you can see that n goes to infinity, and you can see that the rest is positive, so we can write this one as just without the absolute sign. You can just write it like this. Now what we can do is we can combine them into 1. So once you combine them into 1, so you can get 1/5 limit n plus 1 over n to the third power. But what do you know about this one? You know that this limit goes to 1 when n goes to infinity. So 1 to the third power is 1. So that means you simply end up getting 1/5, which is less than 1. Okay, so that means by the ratio test, into write this, by the ratio test, the series, the original series, converges. Okay, actually it converges absolutely, that implies converges, so we can just say converges. Okay, so you can see that's the whole calculation. So let's do one more problem. How about this one? B, let's say sigma n going from 1 to infinity, n to the n over factorial n. And also one more thing, you can see that the n3 is kind of disappear because in the previous problem you have n3, but see what happened, you're gonna get n plus 1 or n that always goes to 1. So that's why we don't it's useless, because it goes to 1, that kind of terms goes to 1. Okay, so in this problem again as before, an equals n to the n over factorial n, n to the n of factorial n. So then what's gonna happen, we can do the same thing as before. It's a limit n goes to infinity, a n plus 1 over a n absolute value. So it's a limit n goes to infinity. So let's plug in n plus 1, so that we got n plus 1 to the n plus 1 power over factorial n plus 1. Again, make it upside down. We don't need the absolute sign because it's all positive. Now we're gonna kind of simplify this like in a nice way. So what we do, we have done this before in the lecture, so we can take one term out and write the rest. In the bottom we're gonna pull out one term again and write the rest as factorial n, and this is factorial n, this is n. So now what's gonna happen, you can see a lot of terms get cancelled. So this get cancels with that, and this get cancels with that. So that means you simply end up getting you get the limit n goes to infinity, n plus 1 over n to the nth power. Okay, so what is this? So you can see that so this is different from previous case. We know that the bottom goes to 1, the limit of the inside function goes to 1, but this is to the n power. So this is a slightly different situation. So in this case it's not 1. So what's gonna happen? So what's gonna happen now? This one we can write as limit n goes to infinity. We can write this one as 1 plus 1 over n to the n. Maybe you remember this in Calc 1. This is gonna be e to the whatever number you have here. So you have here 1, so it's e to the 1. So this one become e to the 1, but e is 2.7 something, so that means this is greater than 1, because you know that e is roughly 2.718. So because of that, this is greater than 1. So therefore we can say by the ratio test, the series n over n1 diverges. Why diverge? Because it's greater than 1. The limit is greater than 1, so the series has to diverge. Okay, so those are two good examples. We can do maybe one more just to see when the test gonna fail. So let's look at this example just to show that the test sometimes fail. So yeah, actually before that I'm going to give you an exercise problem, so you can try this one. So this is an exercise for you. So limit n going from 1 sigma n going from 1 to infinity 2 to the n over factorial n. You can try that. So this is the third example, example number C. Limit n going from 1 to infinity ln n over n, a n equal ln n over n in this case. So let's do the same thing as before. Limit n goes to infinity, a n plus 1 over a n absolute value. In this case all the terms are positive, so you don't need absolute value, so we can write ln n plus 1 divided by n plus 1 upside down ln n. What we can do, we can combine like terms, so that means limit n goes to infinity, we can write ln n plus 1 over ln n plus ln n times we can write n over n plus 1, those together. Now what we can do, we can distribute the limit to the 2, so we have limit n goes to infinity ln n plus 1 over ln n times limit n goes to infinity n over n plus 1. So you can see that this both limits goes to 1. Here ln n and ln n plus 1 are getting closer and closer, so that means this is 1. Here again the same thing, n and n plus 1 are getting closer and closer when n goes to infinity, so this is equal to 1. So that means the whole thing goes to 1. So that means in this case inconclusive. Inconclusive. Okay, inconclusive. So that means so we cannot use the ratio test for this problem. But we know that the series n going from 1 to infinity ln n of n diverges by the direct comparison test. So it's a simple direct comparison argument. You know that the test gonna diverge, but the ratio test does not work here. Okay, so let's go to the other one. That's the root test. So theorem, root test. So what's the root test is about? So let's write it. So let sigma an, it doesn't look like an, so I'm gonna make it an be a series, then as before there are three cases. If, but this time we don't divide, we're going to take the nth root of the nth term. So that means if the limit n goes to infinity an absolute value nth root, so we can take the absolute value of the nth root of the absolute value of the nth term. So we're going to call this rho again, if this is less than 1 as before, then the series n converges absolutely. That implies the series n converges. Okay, you can directly write converge, that's okay. And number 2, if the limit n goes to infinity, a n absolute value, the nth root row greater than 1, the series diverges. And the third one, if the limit n goes to infinity, a n nth root equal 1, the test fail. Or inconclusive. Okay, good. So you can see the argument part is the same. Only thing is what we are taking right now is the nth root of the nth term. So that's the only thing is different, but otherwise this is pretty much similar to the ratio test. Okay, now the question is when we're going to apply this. So again, when to use. So when you see like powers like this, for example, like n plus 3 over n to the nth power. You can see nth power like that. So see like you're going to see algebraic expression and then see nth power. Or like terms like this, let's say 2n minus 7, something, 5n plus 3 to the nth power. Or you're going to see some algebraic expression and n to the nth power. That definitely we use the root test for this kind of problems. You're going to see some algebraic expression and you say n to the nth power. So those kind of situations we can use the root test, because what will happen once you take the root, that n goes away. The root power, one of the root power goes away. Okay, so let's try to see this in practice. How about this one? So let's do first example. We can look at this series, sigma n going from 1 to infinity, -1 to the nth power, 3n plus 4, let's say 4n plus 3 minus 3, it doesn't matter, so just say like that, looks good. So this is to the nth power, so that's this n is the indicator that we can use the root test. Okay, so let's use the root test. So we're going to take the limit n goes to infinity, a n absolute value, the nth root, this is equal the limit n goes to infinity, 3n plus 4, 4n minus 3 to the n power, nth root means 1 over n power, right? So what's going to happen, you can see these two get cancelled, so this cancels with that, so so you simply end up getting limit n goes to infinity, 3n plus 4, 4n minus 3, and when you look at the dominating terms, these are dominating terms, you can see the limit is simply 3/4, which is less than 1. So we can say by the ratio, by the root test, the series converges. Okay, series converges. So it's a very powerful test. So if you try to use some other test for, especially for this problem, it's going to be very difficult. Okay, so let's look at one more. How about this one, sigma n going from 1 to infinity, n minus 2 over n to the nth power. It's quite interesting. So here a n equal an equal n minus 2 over n to the n to the n. Alright, so we can take the limit n goes to infinity a n nth root. So it's a limit n goes to infinity n minus 2 over n to the n to the n nth root. So you can see that it's going to cancel one, the outer one. It's going to cancel the outer one. So that means you're going to get the limit n goes to infinity n minus 2 over n to the n. That's what you get. Now we're going to use one other trick that we used before. You know that this limit you can write in a special form. This one is 1 minus 2 over n to the nth power. That means this is simply going to be e to the negative 2. Where the e to the negative 2 coming from? That's the negative 2. So e to the negative 2 means it is 1 over e squared, which is less than 1, since e is roughly 2.718. Okay, so that means series, so by the root test, series converges. Okay, good. So you can see that those problems are really interesting, and then I'm gonna rewrite the result that we use here. So we use the result that the limit when n goes to infinity 1 plus x over n to the n power goes to e to the x. So that's what we use here. Okay, so please remember this result we use this a lot, so again and again, so this is useful, but we can show this soon. Okay, so this is for you to try. So this is an exercise. So test the convergence of this series n going from 1 to infinity 2 to the square root n minus 1 to the nth power. Okay, so what's gonna happen to this? Okay, so for this problem you might need these results. So we know that n to the nth root goes to 1 as n goes to infinity, and then also for any number the nth root goes to 1 as n goes to infinity, but here we assume that x is positive, so you might need one of those results here. Okay, so that is the end of the root and the ratio test.